Okay, so welcome everyone. Welcome Professor Rahul Mangaram to this session. Uh, so you can probably get started. So Professor Rahul Mangaram is a professor at the University of Pennsylvania in USA. And yeah, Rahul, over to you.
Yeah, I just need access to share.
Okay.
I just did. Can you check?
Yes. Okay, can you see my screen here?
Yeah.
Yes.
That is timer on. All right. Thank you very much for having me be part of this very interesting event. Uh, I'm a Bangalore boy, so I grew up in actually very close to ISC near Makery Circle. Uh, so today I want to talk to you about three very exciting, research problems. I would rather like to focus on the problems rather than how we solve them, because the way individual research groups solve a problem is just, a narrower path. The problems themselves are quite interesting here. So, and these are all surrounding, autonomous systems and how do we make them safe. So my research is at this intersection of applied formal methods of how do we mathematically model systems to provide guarantees of safety and performance, control systems, and within the tools that we build, we use a lot of machine learning. So it is not so much of just applying machine learning to solve a problem, but it is really under the hood. Um, and our research has been applied in three different domains of, autonomous vehicles, medical devices, and energy systems. So they do span a spectrum, but the core type of problems we look at are, quite centered around just answering this one question at the bottom: is how do we provide these safety and performance guarantees in these closed loop life critical systems? And so we'll start with autonomous vehicles over here, and this is an example of a Tesla back in 2016. So this minivan was parked over here on the side of the road, and any person could have been able to see it and just gone around it, but they had this tap over here, so not a big deal. Nobody got hurt. Similar thing, in 2016, this car is parked on the side. The Tesla scrapes against it, and you could say, okay, well, it didn't have enough clearance, not a big problem. And then this is all in China in 2018, and the car smashes into a street sweeper, and essentially, 24-year-old, dies on the spot. And then it goes on, to this is just recently Tesla had to recall a lot of. So this is not a Tesla bashing, talk. It's just that they are the only company that have, these kind of vehicles on the road with, regular people like you and me would be driving them. Okay, maybe not me. I can't afford a Tesla, but but the idea is that this is a live experiment. And so all this stuff that people are selling, especially in the West, I would say, on autonomous vehicles, I mean, I find it difficult. We would drive this in Makery Circle traffic, but that's not the point, right? This technology is coming in these vehicles. It is overhyped to a very, very large extent. And but whenever anyone presents something, especially from the industry, I just have one question: who is liable? Is the driver liable? Is someone else? Is the OEM or the manufacturer liable? And they never give you a straight answer. They just keep showing you all these infographics like these, and this 5 levels of autonomy is also a lot of bullshit, because it's really not about levels of autonomy or levels of safety. It should be 5 levels of safety, but it's more like 5 levels of convenience. So and and we are really much more interested in safety than convenience. Convenience is how you get to the market, but so that started us on, like, back in 2015 on this journey of really looking at how do we make a driver's license test for drivers less vehicles. And And so this is some previous work now, and I'll just show you the journey that we had to use to get to go through it. And so back in again 2016, there was an accident where this truck was turning down this highway, and the Tesla car was driving in autopilot this way, and then the car saw the trailer of the truck, but it did not know what to do with this big white box. And so the car just went straight through the truck. Under the truck, the top got cut off, and the person basically died on the spot. But then in autopilot, it continued to drive off the road. It broke through a fence, hit a power pole, and fell into a ditch. So then we said, okay, how can we learn from this? We don't want to just recreate that, but we want to change the weather, we want to change the driving conditions, the environment conditions as it's driving through. And use that, right? So now obviously nowadays a lot of people are using simulation like Carla and LGSVL and many other simulators, but that time we had to build our own from these video games. And essentially we could then extract from the GPU depth buffer a lidar like signal and see that's the truck and this is how the car is driving. And then we said, oh, why don't we use this as virtual sensors? And from any kind of pose, any perspective, we could extract, depth maps. In fact, we could extract, RGB maps, so optical flow maps, and so on, right? And then we could put as many cameras as we liked into that system. All this had to be built from the ground up, not something we could just download off, some simulator's website. And then we had to then do these pipelines, build these pipelines for for segmentation, for SLAM, and then run that in real time to then start to test these vehicles. As these vehicles started to switch to end-to-end driving, then we built a search engine essentially to look through hundreds of thousands of miles of these cars driving, and under the hood is all the formal verification and falsification techniques that are used to then capture when certain properties like loss of tracking or contact or the time to collisions violations are there to capture these situations. And so this is basically an example that is returned by the search engine to say, okay, here there is a failure, and now how do you go and fix this, right? So in reality, you don't get a blue screen. In reality, you have something more severe like that, right? Uh, so following that, then we were like, okay, well, this is 2018 and Tesla has an accident very similar to what some of the situations. I'm not saying that our search engine was accurate in that sense, but this is just to show that these type of failures are very real, where it oversteered and it crashed into the wall, the hillside, right? So under the hood, what we do is for building this kind of search engine, we are first of all looking at these rare events, because accidents, say for example, a death in the US would have an accident in the US would happen every 160 million miles. So people are pretty bad drivers, but they are not, causing accidents that frequently in terms of so this is a issue of how do you search effectively. The second thing is how do you actually search through and find these problems in the software. So we built a tool chain that essentially allowed us to search through these scenarios, but using a combination of falsification and where you're basically eliminating very safe or very unsafe and trying to find the boundary of safe and unsafe operations, and exhaustive verification, which can only work on very small problems. So the falsification was essentially removing a very large part of the search space and then giving the exhaustive verification very small, narrow ranges to look at. And the way we did this was we captured this for multiple driving scenarios and for curved roads, for roundabouts, and so on. And we wanted to isolate what is the source of these problems. And then once we were able to run it through the cycle, we went into high fidelity simulation based on the actual roads that we're going to be testing on. And then we were testing on with our partners in Nagoya in Japan, where we rented out a lane. And then we started testing out these algorithms for real. Was a specific test for a local planner that is looking ahead 100 meters or 100 milliseconds ahead in time, and making sure that the trajectories selected are the best trajectories. And to allow for this, we built a CAD tool chain, a computer aided design tool chain that could take any black box, vehicle, um, the AV stack essentially, and be able to run that, through this virtual world, and then start to run different scenarios. So here we have different specifications that you can have for safety, for comfort, for so like time to collision. You could change the weather options. You could change the different scenarios like T junctions, merges, and then this would actually do this, gradient descent search to identify under what conditions do the vehicles have very low robustness. That means they're going to come into contact with probability, and then we start to isolate scenarios using this kind of tool chain. So this is an example of one of the projects, within the Department of Transportation, National University Transportation Center, called Mobility 21, which I head at the University of Pennsylvania. And this is in collaboration with Carnegie Mellon University, where I used to be. And this is the third such center that we have been running. This is a $14 million center with multiple projects in them. And as part of this, we also build, like, 1/10 scale autonomous racing cars. I'll go through this rather quickly. The website is just f110th.org. And this we provide, we have fully built, open source autonomous racing platforms. There's an entire autonomous racing course going from, perception, planning, control, learning, and vision, everything. And there are no exams, there are just races through that. And there are lots of algorithms that work very well on these race cars, and like model predictive control, hierarchical learning based model predictive control, end-to-end DNN. It's not a hodgepodge of things. It's a very structured system for perception, planning, and control. And these algorithms have been working for quite a while within this. We host international races. In fact, the next race will be in October as part of a IROS robotics conference. And both, it'll be virtual and if possible in Prague in person. But the virtual races have been really very exciting. And we have a bunch of different simulators, both visual and OpenAI gym-based headless simulators to conduct a lot of different research studies and races on these platforms. Over the last 3 years, we have built in AutoML, in ICRA, using looking at how do I balance safety and performance. And in order to do that, I need to be able to estimate what is my opponent's driving behavior, and then in real time decide based on that, how do I now synthesize trajectories to basically overtake that opponent successfully. So I'm really understanding what is the risk uh, profile of this opponent, and then coming up with overtaking strategies. And this works also on the real platform. It's not just that is the mathematical basis, the simulation evidence, and the actual demonstrations. uh, so that was an example of how do I optimize my racing line, my vehicle dynamics, and my path planning algorithm all together in a super optimization tool chain to come up with the optimal racing line. And the whole idea of this kind of research was, how do we go from just this narrow kind of focus of what I started with, to then putting all of these systems building blocks, so that then students can really understand what it takes to build autonomous systems, not just vehicles, right? And And then with these different partners over here that are there are over 60 partners that use F110 internationally also. We've built a very nice open source community, and that's one way to get involved with that. The second sort of focus areas on medical devices. So I know I'm switching gears quite a bit, but here our interests are in model-based design, but for physiological closed loop control systems. And we want to use formal methods to again provide the answers to the question, how do we guarantee safety and efficacy of implanted medical devices to begin with, right? And implanted medical devices. Right now, actually, this slide hasn't been updated. The latest numbers are more than 18% of all medical device recalls are due to software issues. And essentially, the problem here is that these devices, like a pacemaker or defibrillator that are implanted in your body, and the catheters are put inside your atrium and the ventricle of your heart, they essentially just tested in open loop testing. Like they just give them tape tests. And but what we want to do is we want to test them with actual physiological signals and evaluate them in a closed loop to see how the heart responds to the device, how the device responds, and whether sometimes the device actually can drive the heart into a very fast rhythm. And so we built initially a heart on the chip model that was able to then do this interaction and then do testing and verification of this. And this was a formal model based on timed automata. And so we could do extensive verification of the interactions between the device and the heart. And then the next level was, okay, well, that's just for one device and one general heart model. When you put these devices, you set them to go into the market, you have to go through a clinical trial. And usually clinical trials for these devices take 4 to 6 years, cost anywhere from 20 to 30 million dollars, and more than 35% of these trials fail. So then we said, okay, well, how can we use our heart model, but now not just a single heart model, we generate tens of thousands of these heart models and variations of them, and feed these signals of these devices to them to understand, what is the robustness of these algorithms? When do they fail? When do they actually cause the patient to go into unsafe conditions? But looking across large populations where you have intra and inter-patient variability. And so this is the ideas here, is to say, well, before you do a clinical trial, can we do a virtual, or a computer aided clinical trial to get some initial insight into how the trial is going to come out? What is the outcomes of the trial? But for that, if you're using models, you need to understand what is the uncertainty inherent in the models, what is the uncertainty inherent in the outcomes that you are proposing over here, and have a very formal statistical framework that you can then take to the regulators, so they use your virtual population as regulatory grade evidence to say, instead of having 2,000 patients in the trial, they can replace 200 of those patients with 11,000 of our virtual patients. Virtual patients are much cheaper, and most trials also fail because patients just drop out, right? So this approach was really asking these questions of how do we capture this model uncertainty? I'm not going into the details of it, but that's the main question. That you are using model-based approaches, but you're also introducing a lot of uncertainty based on your models within this. How do you come up with a statistical framework that captures these uncertainties as they go through your pipeline? The second question we wanted to ask over here is, how do we then combine, statistically combine virtual and real patient data to then have, a combined cohort that can then provide, much better insight as to how well this device is working. The third contribution was to say, okay, now that you have combined these real and virtual cohorts, how can we use that to isolate low robustness? That means where the algorithms are very weak or very sensitive to parameters in the patient population, where that causes the device to do a misprediction and to shock the patient instead of not shocking the patient, or to not shock the patient when it needs to shock the patient, uh, as these devices work. Uh, a third problem that we look at right now is that is with a condition called atrial fibrillation, where the heart starts to beat in a very chaotic manner, and several million people die, and especially Indians like us. We have high blood pressure, diabetes, and atrial fibrillation is right up there as one of the killers, right, for us. So this is a very important problem, especially for us. So essentially, what the physicians have to do is they find this chaotic behavior in the heart. They have to go in and burn the tissue. So they basically, from the groin area, they put catheters, and then they have RF, high frequency RF catheters, and they ablate. They burn the tissue to basically close any kind of circuits, electrical circuits that are causing re-entry, or for the heart itself to kind of have some kind of resonance. And so it's basically these physicians are electrical engineers plus surgeons, and they are trying to find these kind of electrical circuits and burn the tissue over there. But this is a very kind of expertise based issue, that where if the physician is very good, then he can diagnose it. So what we are building now is a way to guide physicians by building personalized heart models, where we take the heart model, the measurements that they take from the surgery while they're doing the surgery, right? And then in real time, we're able to then capture executable heart models, which we can then run many scenarios on, and then help them guide them to say, this is where you need to ablate, this is where you need to burn the tissue with high probability, and then this is the part that will terminate this condition. It's a very difficult problem. We are not there by a long shot, but we are at least in the first stage where we can capture high spatial resolution and very time synchronous whole heart models to then run these kind of and then there's a lot of the main questions that we are asking is how can we speed up the procedure, because now the physician does not have to have such cognitive overload to know where to ablate, and how can we then provide very accurate and precise ablation vectors where they need to go and burn the tissue. And so this is really making it faster, making it more precise, and then also making some kind of termination confidence that this is going to terminate atrial fibrillation after it's done. So we had to build these very mathematically intense models that under the hood they capture the electrophysiological behavior of the hearts, and then they can be automatically tuned to each patient. And so we are able to get highly accurate models within 5 milliseconds accuracy of real patients, and capture these. And now we are on the next stage of how do we help the physician do anything. Of course, again, we are in this model based world for these life critical systems, and we need to just make sure that we don't drink too much of the Kool-Aid. We really have a grounding, that we work with the physicians in the operating room, we work in our computer science lab, and we go back and forth, and and that keeps us very real. The last part, I know I have only 7 minutes left, but is on energy systems. And here our focus is on, again, a big change from the first two parts, but hey, what the hell, right? May as well have fun here. Is on bridging machine learning and control for smart buildings, right? And so let me motivate this problem, right? So in the US, now you can see there's a lot of, and we are seeing these heat spikes everywhere, right? The very, very hot 47 degrees centigrade spikes in many places around the world. So back in 2015, there was a spike in July, and the price of electricity, which is normally $25 per megawatt hour, spiked to $800 per megawatt hour, because air conditioners are on, everything is, plants are basically shutting down, generation plants are shutting down, and demand is at all-time high. So the price in the US market in California went up by 32 times, not 32%, in 5 to 10 minutes. And then in winter, we had this polar vortex, which was extreme cold. in early February, in late Jan, early February, and the price went up 86 times. Okay, 86 times in 5 to 10 minutes. Imagine like you're going to buy like like some upma for breakfast, and they say no, sir, today the price is 86 times of yesterday's price, and you're like, are you out of your mind? But you have no option in this case. So in fact, this price volatility has become the new norm because of a lot of climate change issues. And that's, people say, oh, climate change is 80 years away. No, it's right here. You can see that in the electricity markets. So what we wanted to do was figure out how we can make buildings adapt and be price aware. So, but we want to go from very clunky rule-based control to using model predictive control, but learning these models in a very low-cost manner. So very data-driven model predictive control models, so that we can adapt the building's usage, that when the price spikes, we can curtail. And so essentially we want to have all these nice things of energy efficient control based on that is very price aware. And I'll remove skip this marketing slide. But essentially the idea is, the main problem is, in order to control something you need to have a good model. And if you're trying to build a white box model or a physics based model, then you have to spend at least 9 months per building, have two experts, and spend $120,000 on just building that model, and you're never going to recover that money from the energy efficiency of that building. So because you have to go floor by floor, wall by wall, equipment by equipment, build up these high fidelity physics based models, they're too huge. They have hundreds of thousands of parameters, and they don't even converge. You have to do lots of guessing after the model, because the buildings are messy. Nobody has like made a building so you can have a really nice physics based model for it. Um, so we took this one building that took us 9 months to model in a physics-based approach, and then use data-driven approaches to predict the energy. And we could do that in 6 hours to get a 96% accurate model. And then we wanted to see how this works for 200-year-old building, clinical building, physics buildings, Wharton Business School buildings, and we could get anywhere from 96 to 98% accuracy on how this building is going to work using different approaches, starting with random forests, and then we moved on to using Gaussian processes, which I'll talk about briefly. And essentially, as the price is spiking, you want to have this demand flexibility. And in the US, if you have this kind of demand flexibility, you can actually earn money, because it's kind of a negative load in the market. And instead of having curtailments or load shedding, you're doing a very fine grained load shedding over here. And so coming back to the technical points, right? I mean, we want to first conduct optimal experiment design on how to get a high fidelity data driven model of that building. And we have all these basic questions: how much data, how do you run these functional tests? You're going to sort of do system identification on a building, but you can't disturb the building. So how do you design these functional tests to get an accurate model? How do you provide performance guarantees? How do you run this energy optimization problem? And then as the building lives for another 20 years, how do you keep updating your model and working with that, right? So for the first part, we had essentially for this part, we had a couple of best paper awards on how to do this kind of very efficient and online learning approaches for this control problem, where you have a building, you want to manage the peak power consumption, but you have manipulated variables, like things that you can change, like cooling temperature, supply temperature, your whole HVAC loop, and things that you can't change, like the weather, occupancy, and so on. And so we want to learn a model of that and be able to manage the peak, minimize the peak power consumption, or minimize the overall power consumption in some time. And so we have to set up this model predictive control, traditional model predictive control problem over here. The problem is that our model is based on the data that we are getting. So we want to go from this physics-based model that takes 6 to 9 months to go to a data-driven model that goes, that basically takes 6 to 9 hours, like that, right? So, and we want to have other things also where we can interactively manage this model. So control and prediction with machine learning are kind of the complementary problems where in one case you're given the control variables and you want to predict the outcome, and that's a machine learning problem. But in the control problem, what we want to do is we want to say, well, this is the outcome that we want. What are the control variables? But we want to this is subject to the learned models that we have captured in terms of the observation of how the building responds. So this is a very difficult problem. It's mostly non-convex, sometimes non-differentiable, and there's no closed form expression. So usually people resort to kind of greedy or genetic algorithms to solve that, right? So I'll wrap up in 2 minutes. Um, so we started to use Gaussian distributions because that gives us a much richer, probability distribution as to what is happening with the building. And we could work with small data sets, and we could use a prior knowledge when we do functional tests on the building. And so without going into the details of that, I'll point to the paper. We are able to then work with real buildings to then curtail and provide these cost savings, in real time, and provide a dashboard to the occupants to say, hey, we can automatically do this curtailment, change your fan speeds, change the compressors, automatically do the whole thing custom to your building and save you, a certain amount of money over the next 2 hours. And we could do this for a microgrid, which has many buildings in it, and a hotel, grocery store, factory, all of that that were part of this system. And each building operator could see what we are going to change in the next 2 hours and what the temperature will be, and accordingly they can choose which strategy they prefer and how much savings they want. And we could generate many alternate strategies for them for curtailment, and they could choose one that keeps them still comfortable but also saves them money. And you could have custom comfort conditions, say the CEO's office floor, don't touch it. Where grad students are, don't worry, you can make it very hot or cold, right? Just a joke. So this allowed us to then focus on how do we then do this online updates to the model and do online learning. And I'm going through this very quickly, but essentially with Gaussian processes, we designed an approach that minimize the variance and maximize the information gain for every additional data point that you get to decide how to update our model. Because with Gaussian processes, you cannot have a very large training data set because of complexity reasons. So we were able to then run that for the building. And as the building was running, we could then start to lower the error from the first 3 weeks to the second 3 weeks of our actual building then, right? So that just concludes this last part, that problem 3 of bridging machine learning and control. And this is a link to that paper over here on learning control, and I can share the slides later on. But just this wraps up, looking at the 3 problems in designing safe autonomous vehicles, safe autonomous medical devices, and then in kind of looking at physical control systems for automation in building, like building automation. I can stop here.
All right, thanks a lot, Rahul, for the excellent talk. So I had a question regarding the first part of the talk that was on autonomous driving. So you showed videos where there is a static vehicle standing, and then this autonomous vehicle sort of goes and ramps in. What happens if the autonomous vehicle is driving and someone kicks from behind? I mean, is there a way to navigate around such behavior?
Somebody hits you from behind?
Yeah.
So first of all, legally, you are not at fault if somebody hits you from behind.
No, how do you sort of navigate around? I mean, how do you detect and sort of make maneuvers that help you avoid this situation?
Yeah, that's a very good question. So right now, what our research is focused on is what we call learning and improvisation for autonomous racing. And that's where, the reason we focus on racing is because you have very adversarial interactions between agents like that, right? So essentially you cannot crash, but you have to maintain a high enough speed to win the race. And so this allow the traditional way in which people look at this problem is by building, they use an inverse perspective mapping, where essentially you take all your cameras, lidars, and you do sensor fusion to build a bird's eye view, and that allows you then to do behavioral prediction and planning with full situational awareness. Right, and that's what all the car companies are doing today.
Yeah.
It's just that rather than using traditional geometric computer vision for inverse perspective mapping, they now have very large neural networks to capture these bird's eye view to do the behavioral planning.
All right. So fine. So there is a question in the chat box. This from Jayabrata. So he's asking whether the simulator for testing the autonomous vehicle open sourced and what kind of software stacks are used to build that, like ROS or something else.
Yeah, so we for the 110 scale platform, everything is open sourced, and you can get all of that on this website. I'll share the link in the chat, f110.org, and that's a very good place to start, both as virtual simulations and driving at 110 scale. If you want to have a full-blown vehicle, then you would have to start with AutoWare. AutoWare is the meta operating system for a autonomous vehicle software stack, and we are a premium member of the AutoWare consortium, and they are using F110 as a rapid prototyping system. And this is much more. It's 1,000 times cheaper than building your own autonomous vehicle. Um, and so F110 is a good place to start. Simulators, course materials, the AV stack, everything is there. It works with LiDARs, depth cameras, stereo cameras, all of that. Perception planning control, all of that is part of it.
All right. Thanks a lot again, Rahul. On behalf of everyone, I take